All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Hopefully you guys are doing okay. Last time we had some technical difficulties, so I kind of spoke about the topic we're going to do, related rates, but things got messed up in the middle of the first example. I wanted to give you guys an example so you guys could try a bunch of problems and we go over them together. But we'll just kind of try to do all of them in today's class, I suppose. So that being said, let's get it done. And there we go. So yeah, more related rates. We spoke about it very briefly last time. I guess I will go over it a little bit more now, but we had technical difficulties, and so we never even got through one of these. I will say I did go through some of these problems in my other class as well. So I can say preemptively for now, you are going to have to coming in. You need to remember implicit differentiation. It's a very important thing here. Okay, so in some ways, related rates is an application of implicit differentiation. Just to quickly remind ourselves, when two quantities are related, mathematically, it turns out that their rates of change are also related, and you can figure out this relationship between the rates of change by just differentiating the equation. If we think of time as the independent variable, we can differentiate any equation that relates a bunch of variables, and we can get an equation that relates their rates of change. And the idea is sometimes we know about the rates of change of some things, but not something else that we care about. And so we can use the related rates to figure out the rate that we want to find. So related rates problem are one of the types of word problems that will come up in this class. Of course, you do need to know when you're being faced with a related rates problem. What I just sort of said is what's going to be described. You are going to be told about several related quantities, and you're going to be given the rate information of several of them, not all of them. And then you're going to be asked to find the rate of change of one of them that you weren't given. Now, once you recognize that you're looking at a related rates problem, you move on to the 6-step method. Method for related rates, always use this. First, you would read the problem carefully. Make sure you know it's a related rates problem. First of all, there are going to be a bunch of different types of word problems. Then you are going to need to pick out the important information. So reading carefully is going to be very, very important. Second, you're going to draw a diagram if necessary. Make sure you label it properly. Cannot stress this enough. You label things that are changing with variables, things that are not changing with constants. That way, when you start taking rates, you would get the derivative being 0 when you expect it should be 0, and you won't have to worry about it. And you don't always have to draw a diagram. I did mention that in a footnote. The diagram is really to help you come up with an equation that you think will be useful for step 4. But if you're given the equation, you don't have to do step 2. Third step, you want to write down what you know, all the rates you know, and what rate you want to find, and the point at which you want to find that rate. This is just to give you a goal. And actually, once you have the diagram and you write this goal down, you can actually ignore the original word problem. It's now a matter of getting all that stuff to work together. So the fourth thing is you're going to set up an equation. Your diagram can often help with this if it's not given. And then you are going to differentiate that equation with respect to time. It is very important that you know time is always the independent variable. T, always the independent variable. What this means is you're doing implicit differentiation. So if you're differentiating any variable that's not a t, you need to multiply by its derivative. You need to multiply by the prime. However, in this case, I would tend to use the Leibniz notation. Maybe I should actually meant to mention that. It's not that it's right or wrong, but I think it's good to always remind yourself that t is the independent variable. So when you see that dt on the bottom, it reminds you, as well as, you know, in the future, the prime notation gets less and less useful because eventually you get to a point where you're dealing with several independent variables and you want to identify which one you're differentiating with respect to. It's not something you guys have to worry about. That's like a Calc 3 problem. But we'll tend to use Leibniz notation here for clarity. Right. So you guys know me. I'm partial to the prime notation, but that's because it's easier to write and I'm lazy. But even myself here, I always use the Leibniz notation. So I think it's a good practice in general. Now, once you differentiate, you now have an equation that have all the rates of change in it, maybe some other variables too, and you can have the rate of change that you care about in this equation as well, would be the point. So what you're going to do is now you're going to plug in your knowns and solve for your unknown. Then there's a potential issue that can happen here. There are times when you get to this point and you don't have enough knowns to find your unknown. Maybe there are several unknowns. And in that case, what you do is, you know, you just panic. You say, oh my God, I'm going to fail this test. I'm not going to get to med school. My parents are going to do something. No, you don't do that. You never panic. You never panic. That was a joke. Do not panic. You go back to step 4. So for step 6, may need to go back to step 4. And that happens particularly when you're missing some information. You're going to see some examples where this happens, right? We're going to do a bunch of examples. Okay, but that's the process. You go through this 6-step process all the time. You're going to see that every example I do, I'm going to go through this 6-step process. I would just have this process kind of memorized and drilled in. You do a bunch of practice problems. It should be drilled in by you get to the end. Of course, you don't have to memorize this entire table. With enough practice, you'll be able to just memorize the phrases that I have in bold, or maybe even smaller phrases than that, and you will know what to do. So when you get to a test or a quiz and related rates is there, you should never be kind of stuck or unsure of what the next step is. You're like, wait, what should I do again? If you're like that, you already messed up. You done messed up, right? You should know exactly what to do next all the time. You do these 6 steps in this order every time, okay? So it's we're going to do that now. So what we are going to do is these examples that I checked off, 1, 3, 4, 5, 8, and 10. I'm not sure we can get through all of them today, but we are going to try. And of course, I would encourage you to try the others. Do your homework, find problems in your textbook, do those. The more you get used to this process, the better. Also be aware that you need to remember some formulas from 2D geometry. It's just expected to know, area of a rectangle, area of a circle, perimeter of a rectangle, stuff like that. And yeah, I mean, occasionally I'll give you formulas. That's for something weird, like the volume of a sphere. No one ever remembers the volume of a sphere. I don't remember the volume of a sphere half the time. So yeah, but if it's like a rectangle or a circle or some plane figure, I would expect you to know that. If it's a prism, like a 3D thing that has a shape that's propagated along an axis, I expect you to know the volume is the area of the base times the height. That's why the area of a box, the volume of a box is the area of the base, length times width, times the height. Yeah. All right, so without further ado, let's actually jump into it. Let's see what this looks like. So we're going to move on to problem 1. So a right circular cylinder undergoes expansion. Its radius is increasing at a rate of 1 meter per second. Its height is increasing at a rate of 2 meters per second. At what rate is the volume changing when the radius is 1 meter and the length is the height? I think that should be the length of the height. Or I should have just said the height. Oh no, it's 1 meter in length and the height is 3 meters. Okay, yeah, that's fine. Yeah, so step one is to read. Read the problem. Okay. Reading is fundamental. Step two, you're going to come up with a diagram. In this case, it is a right circular cylinder. And that means it's a circle propagated along some axis. And that axis is at 90 degrees. It will have a radius. Call that R. We call it R because I know the radius is changing. We were told that. And it will have a height. Call that H. I called it H because the height is changing. We were told that. And then, of course, V would be the volume. Okay, so that is our diagram. Moving on. 3. What do we know? What do we want? We know that dr dt is 1 and dh dt is 2. Specifically, +1 and +2 because they're increasing. Okay. What do we want? At what rate is its volume changing when the radius is this 1 and the height is 3? So what do we want? dv dt. When do we want it? Now. No, we want it when r equals 1, h equals 3. Okay. So now we move on to step 4, which is going to be the equation. What's going to be the valid equation here? So we have our diagram. Probably some of you are getting PTSD about it, have nightmares about high school geometry. But this should kind of indicate to you what the formula is going to look like. It will be the area of the circle times the height. So V equals pi r squared h. So that's our equation. Moving on, 5, we want to differentiate. And I'm not always going to say this, but the derivative differentiation is implicitly with respect to time. Okay. All right. So how would I differentiate this equation with respect to time? Someone help me out here. Differentiate this equation with respect to time. What do you get? Anyone? Bueller? Yes? Go ahead. Don't be shy. I have a lot to get through, so just let me know.
I'm not sure, but to start dv over dt equals
Yeah, that's
2 pi r, and then I'm not sure about the h.
okay. So what is R and H? How would you describe them?
Measurements.
Sure, but are they constants? Are they something else? Are they constants or are they changing?
They're changing.
They're changing. According to what? They're changing over time, right? So we're told how they're changing over time, which means we're thinking of these guys as functions of time. These guys are functions of t, right? That's what I mean by implicit differentiation. You really want to think of that. The t is the independent variable. Every other variable is considered a function of t, right? So this is some function of t. This is some function of t, right? That's what it means that t is the independent variable. Every other variable depends on t. Okay, so now that I told you that, can you finish up?
Like you would do product rule then?
You do the product rule. Exactly. So here you would need product rule. So that should tell you what you should do with the h. So now we have dv dt equals, what would you get now?
2 pi r h plus pi r squared.
No, not quite. Can someone help Anthony out? What is he missing? Does anyone see what he's missing?
H prime.
Okay. Is that the only thing? Who did you differentiate in the first term?
It should be r prime too.
You need an r prime. It's implicit differentiation, and t is the independent variable. Right? Like you need to remember how to do implicit differentiation. Go back and review it. Like I don't really have time to teach it again. If you differentiate anything that is not the independent variable, you need to multiply by the derivative. We just differentiated an r. You need to multiply by dr dt. In the second case, you differentiated an h. You need to multiply by dh dt, right? It's implicit differentiation, right? So that's what we have. Now, we actually want to find this guy. To solve for this when r equals 1, h equals 3. How do I know that? Well, I wrote that down in step 3. I want dv dt when r equals 1 and h equals 3. Right? I don't even have to look at the word problem anymore. Move this guy out of the way. Okay, so that is the derivative. So now I will go to the 6th step, which is plug in. And so I have dv dt, which is the guy I want to find. Now I'm going to plug in all the other guys. It's 2 pi rh. I know my r is 1 and my h is 3. So it's 2 pi times 1 times 3 times dr dt, which I know is 1, plus pi times r squared times dh dt, which I know is 2. Now I'm plugging them in. This is going to be, of course, 6 pi plus 2 pi. And so our dv dt is equal to 8 pi. Like I said, in this class, I don't particularly care if you have the units, but since we're here, it's meters per second. So the volume is changing at 8 pi meters cubed per second. Okay, so here were the 6 steps. 1, read. 2, diagram. 3, what do you know, what you want. 4, equation. 5, differentiate implicitly with respect to time. You need to review implicit differentiation. And 6, plug in. In this case, everything went smoothly. Yeah, so that's that. We're going to do this a bunch more times, just to kind of hammer it home. Okay. Maybe I will want to do anything semi-productive. Switch to the Windows one. Let's make these questions a little bigger. Maybe a little bigger. Okay. All right, a 15-foot ladder rests against a vertical wall. Suddenly and without warning, the foot of the ladder begins to slide away from the wall at a rate of 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? You should read this and know it's a related rates problem. They told you about the rates of change of something and they asked you about the rate of change of something else. And these two things are obviously related. They relate to a ladder. So 1, read. You know it's a related rates problem. 2, diagram. Does anyone see what the diagram is going to look like here?
A right triangle.
It's a right triangle, right? You're going to have a vertical wall and you're going to have the ground here. It's vertical means this is 90 degrees. And then you're going to have the ladder leaning against that wall here. Right? And so we end up with this diagram. It's just a right triangle. And I can label this right triangle. Let's say I label this X. And the height Y. What do I label the hypotenuse? I just did X and Y for like the X and Y axis. That's what I thought about. What about the hypotenuse? I don't know if you can see the problem. What would you label the hypotenuse?
Z.
Do we agree? So go back to that table. Which eventually you'll have memorized. And reading that, you see that, okay, possible or necessary, draw a diagram, label quantities that are changing with variables and quantities that are not changing with their constant values. what would you label the hypotenuse?
$15.
15. Okay. Now, we could label this as Z, but issues arise in practice. We'll discuss later. Okay. So while it's technically not wrong to call it Z, I would definitely recommend don't label anything a variable that's not changing. The length of the ladder is not changing. Don't call it Z. It's not moving. It's 15. It will always be 15. At the end of the problem, it's going to be 15. The beginning of the problem is 15. All the way through the problem, it's 15. Label it 15. Okay. So now that is our diagram. So we'll move on to step 3. Write down what we know, what we want. What do we know? We know the foot of the ladder is sliding away from the wall at 2 feet per second. So X is changing by 2. It is positive because X is increasing. Right? If the foot is sliding away, right? If the foot of the ladder is sliding away, X is getting bigger. So it has a positive 2 rate. And what do we want? How fast is the ladder sliding down the wall? That's how fast the vertical height is decreasing when the foot of the ladder is 9 feet from the wall. That's what we want. Now we move on to 4, which is to set up the equation. So you look at this diagram. What do you want the equation to be? Knowing that your diagram gives you a right triangle and you have all the lengths of the sides.
Pythagorean theorem.
Pythagorean theorem, right? See the picture, you drawing the picture and visualizing the situation helps you come up with the equation. Pythagorean theorem. We know that the sum of the squares of the 2 legs is equal to the square of the hypotenuse. That's kind of big, right? X squared plus y squared equals 15 squared. So that's our equation. 5. We're going to differentiate. Okay, differentiate that equation. What do we get?
Um, 2y prime plus 2x prime.
2y prime plus 2x prime.
2y times y prime, sorry,
Okay.
plus 2x equals 0.
So you want 2x plus 2y y prime, which I'd write as dy dt here, equals 0, like that.
Yeah.
Okay. That looks fine. Who is the independent variable?
T.
T. T is always the independent variable for this problem. If it's a related rates problem, T is always the independent variable. Do we still stand by this answer?
So it's 2x times x prime.
You need an x prime because x is not T. It's not an independent variable. It is a function of T. So it's 2x dx dt. Okay. Related rates, T is always the independent variable. Anything other than T is what you have to multiply by a prime, including x. I know you're used to x being the independent variable. Doesn't apply here. T is always the independent variable for related rates. Okay, so now we have that. So now we go to step 6. We're going to want to plug in. We want this guy. So let's actually see if we can get that. So we go in and we know what we want and when. We want dy dt when x is 9. So I'm going to go in. I'm going to plug in 9 for x. For dx dt, plug in 2 plus 2 times y. We don't have y. And then my dy dt. Hold on a sec. I have two unknowns here, right? There's the one that I want, the dy dt, and there's a y. So I have one equation and two unknowns. What do we do? Panic. Jhevon, do you make a mistake in this problem? I don't think we have enough information. No. Whenever you get to step 6 and you don't have enough information, what do? Well, if you go to back to our table, at first you may end up with several unknowns. In this case, you should be able to go back to the equation in step 4, solve for all the unknowns, and then come back, right? So whenever you're in this situation, you don't panic. You don't think something is wrong necessarily. You just go back to step 4. Now in step 4, we know that x squared plus y squared is 15 squared. So when x equals 9, this means we have 9 squared plus y squared equals 15 squared. So from this equation, I can solve for my y. There are many ways to do this. You can notice that 9 is 3 times 3. And y squared, and then 15 is 3 times 5. So this would mean that your y must be 3 times 4. That is because of something called a 3-4-5 triangle, right? So we know that's something we know from high school geometry. There are these numbers called Pythagorean triples that they kind of always come in triples whenever you have a right triangle. 3, 4, and 5 are such numbers. If the length of one side of a right triangle, if the length of one of the legs is 3 and the other one is 4, then the hypotenuse must be 5. It's just something that you know. Another one is like the 5, 12, 13. Right, so that's 25, 5 squared plus 12 squared. That will be 25 plus 144. That gives you 169, which is 13 squared. So 5, 12, 13 often come together. The nice thing about these triangles is that by similar triangles, you can make it proportional. So you can it keeps the relationship if you multiply each term by a non-zero constant. So if you have a 3, 4, 5 triangle, I can go through and multiply each term, each length by 3. And then I would end up with a 9, 12, 15 triangle, right? So we have that. I mean, otherwise you could just brute force it if you want. Otherwise, you would just do y is equal to the square root of 15 squared minus 9 squared. And yeah, you have fun with that, squaring 15, subtracting 81, and then finding the square root of that. But you can notice these little patterns as well. So it's a 3, 4, 5 triangle. So at the end of the day, we do know that our y equals 12. So now you go back to step 6. All right, so step 6, we were the 292. Plus here now we know that's 212. 292, 212 dy dt. Right, so we have that guy. Let's move this guy out the way. Okay, so we have this. And now we want to solve for this guy, the green. He's now the only unknown. You can actually divide both sides by 2 right away. And you would get that your dy dt is equal to minus 9 times 2 divided by, well, 12. You can say 2 into this goes 6 times. 3 into 6 goes 2 times, 3 times. So this is minus 3/2 feet per second. Is it feet per second or per minute? Feet per second. Right? We got a negative answer. Is that, did we make a mistake? I mean, did we do an error?
No, because y is getting smaller. So
Y
it's
is getting
negative.
smaller, right? So if the foot slides away, the Y is going to get smaller. This guy is going that way. So it's sliding down the wall, the Y is getting smaller, so the Y is decreasing. So you should get a negative. So this makes sense since Y is decreasing in this scenario. If you didn't get a negative, that would be wrong. And if you get to this point and you're like, oh, you start panicking, you thinking you shouldn't have gotten a negative, and then you just randomly erase the negative, you would get that wrong. So you do need to understand what's going on. Okay. So that's another problem. But as you can see, again, went through the 6 steps. Read, diagram, what we know, what we want, equation, differentiate, plug in. Here we had that little hiccup with the plugging in. So you just go back to step 4, you find what's missing, and then you come back to step 6. To mention the issue I spoke about, so here is the potential issue. You're not guaranteed to fall into this, but it happens a lot. I see it a lot, which is why I recommend against it. Like, of the hundreds of calculus papers I've graded, thousands at this point in my life, this happens way too often for comfort. So for the past couple of years, I've been recommending against doing something like this with the x squared plus y squared equals z squared. Why not? Well, when you get to this point, you would have 2x dx dt plus 2y dy dt equals 2z dz dt. And what ends up happening is that students often get confused by these two guys, especially when they're in a test, they're not thinking straight, they're anxious, they're rushing to try to get through the problem. They come and they ask me, oh, we don't know what dz dt is. You didn't give us that, or something like that. But the solution here is, of course, that your dz dt is 0. Why is it 0? Because z is not changing, so the rate of change is 0. And so, but dz dt equals 0. This is often not recognized at this stage. And then students get stuck here and they say they can't do it. So I would just avoid it altogether. Even if you're not going to get stuck, why give your brain the extra hurdle? You know what I mean? Like, you need your brain power and motivation for the rest of the test. Like, why are you going to have your brain worrying about what z and dz have to be to make this make sense in the first place? It's just not necessary. And so that's the potential issue, why I recommend against labeling things that are not changing with their constant values. Okay, let's see. Maybe we can get through one more. Let's see. And all right, we're going to do this one rapid fire because hopefully we sort of get the idea. There's nothing like different. It's always the same 6 steps. You know what I mean? Right. So let's just quickly go through. The volume of a sphere is increasing at a rate of 5 cubic feet per second. How fast is its radius increasing when the radius is 2 feet in length? The volume of a sphere of radius r is given by this formula. 1, you read. I know this is a related rates problem just by how it's described. 2, diagram. At this point, you realize, hey, not necessary. Equation given. So you move on to 3. What do we know? What do we want? We know that the volume is increasing at 5. We know that dv dt equals 5, plus 5 to be exact. What do we want? How fast is the radius increasing when the radius is 2 feet in length? We want dr dt when r equals 2. Moving on to equation 4, equation. We're told that it's v equals 4/3 pi r cubed. This was given. And so 5, go to differentiate. So here we get dv dt equals 4 pi r squared dr dt. And we want this guy. So 6, go to plug in. you can have dv dt is equal to 5, 4 pi r, 1 r equals 2, dr dt. So this implies that 5 is equal to 16 pi dr dt. And so your dr dt is equal to 5 over 16 pi. And that is in feet per second. Okay, that's that. Went through the 6 steps again. Step 2 was not necessary because I was given the equation. So that there's an example of when you don't need it because you're given the equation. Yeah. I think we'll stop there. But related rates, definitely something you want to get used to. So what I would say is definitely try the rest of the examples on your own if you haven't already. Let me just paste them all here. Try these for next class. So now, hopefully that jogged your memory enough on implicit differentiation, and you got the feel for the process. 6-step process, always the same process. T is always the independent variable. You're always doing implicit differentiation, and you always go through these 6 steps to solve a related rates problem. Try it on those 3. We'll finish those up tomorrow. Hopefully we can move a lot quicker, and maybe we can start introducing the next topic, which is going to be max and min values, if I recall correctly. But yeah, we will stop there for today. Yeah. And again, these will be in the class notes. They're also in a handout on the class webpage. So yeah, should be able to get to those. That's kind of it. That's all I have to say today. So have a good rest of your day. I will see you guys tomorrow in the next one.